So we'll be beginning up with the dynamics of a rigid body. Essentially what we do over here is we take a rigid body and then we want to apply the equations of motion on it and then understand the dynamics concerning these motions. Now they may be due to the action of a load, or in a more general case due to thermal effects or other mechanical loads combined together, but the idea remains the same. Okay, and again, as we have discussed, a body may not exactly be rigid. In fact, no body is exactly rigid, but it can be modeled as a rigid body depending on our application. Okay, so there is one specific definition which should be brought out over here since it's relevant to dynamics. Okay, so in a rigid body, model. Okay, I hope you can notice how I am now sneaking this word model into this. The transmission of forces forces from one material point to another is instantaneous. Okay, this is not for a deformable body. Okay, a deformable body, for the force to be transmitted from one material point to another, it will require some time. Okay, and it happens through many different phenomena which we cannot discuss at this particular time, since you all are in your first year only, but I think this definition itself should be sufficient for now. Okay, so before we sort of delve into it, we have to define a very important quantity called the inertia of the inertia as a matrix. So let me do that over here. I want to write the moment of momentum about a point A of a rigid body. So let's take up so you have your E2, E3, E1, then you have this mass dm, okay, let me just try to draw slightly more. Yeah, so this point is P clearly. Fine, and we are all in so-called M. Okay, mass is M, frame M. Okay, and this has an angular velocity of omega. Since we have to deal with the Euler's axioms, many of the things will be terms of inertial frame, and we'll perhaps specify it as and when it comes out. Okay, as of now you have this point A, that point about which we have to find the moment of momentum of this rigid body. Okay, and we have drawn E1, E2, E3 axis on it. So A is be a material point, or it can be on its hypothetical massless extension. Either of these two cases are okay. So at this point we are saying everything in respect to an F frame, and we will invoke the inertial frame when we need it. Okay, so when we need to use the Euler's axiom. So right now actually for these definitions what we are about to do, we don't require the frame to be inertial. So this F frame is there, but we will not be writing this F everywhere. Okay, so that is something which you have to get used to, but per se it's not inertial frame. Okay, now you have points P and A of this body. Let's write the VPA is equal to VP minus VA. This can be written as omega cross RPA. Okay, now we can say HA RPA cross VPA DM cross RPA DM. Okay, so VPA can be written as omega cross RPA according to this over here. So that's the moment of momentum of about A for this whole rigid body. Okay, in one word. So the total mass is m, and we are writing it for the small mass dm, then integrated over. Okay, let's try to expand some of these expressions and perhaps get to a more uh, helpful formulation of HA. Okay, HA in itself, this is correct. Okay, there's no doubt about it, but we want to write it in slightly more useful form. So the rest of this exercise is towards that. Okay, so let's call this omega vector as, in terms of the E1, E2 and E3 basis vectors, we can write it as omega I E I hat. Since I is a repeated index, so it will be repeated from 1 to 2. So omega 1 E1 plus omega 2 E2 plus omega 3 E3. Okay, that's how this vector is written. Similarly, the vector RPA can be written as xi ei hat. Okay, now we want to write RPA dot RPA is equal to R square is equal to x1 square plus x2 square plus x3 square. Just take a dot product with this one, and okay, RPA, then you have RPA dot omega x1 omega 1 plus x2 omega 2 plus x3 plus x3 omega 3. This is xj omega j. Okay, so HA over here should be, now we want to substitute, let's write M. Okay, we want to write it as let's look at this one. Okay, this expression for HA. So we want to use this formula of a scalar triple product. Okay, and then vector triple product. We have used this before, so this is not the first time we are using. Minus RPA dot omega or PA dm. Okay, so you should be able to write this using vector triple product. Please recall the formula for it if you do not know it. Okay, we have done this, so I'm leaving this in a red for you, so you should be able to verify that you actually get this. Okay, fine. Now since this is a vector, we can write its ith component. So HA, as you know, is a vector, so this can be written as HAI EI hat. Okay, so I want to write its HAI is equal to M R square omega I minus xj omega j xi dm. Okay, because this RPA dot RPA is actually equal to R square. Okay, and omega will be a vector, so that is true. Now RPA dot omega will be xj omega j. Okay, and then you have RPA, which is xi. So the ith component of this can be written in this form. Okay, and how do I write the ith component of, say, omega? Quite simple. Let me use another ink. I write ith component of omega by writing at omega dot ei. Similarly, I can write this as omega j ej dot ei. Okay, and then you have this omega has been written like this, and then this omega j ej dot ei can be written as omega j delta ij. Remember, ej dot ei will be equal to delta ji, or this will be equal to delta ij. So I hope you can recall all this. If you cannot, please pause the video and go back to the discussion on index notation. Okay, once this is done, now we also want to write this omega I should have written it here itself, omega I in terms of omega j. Okay, so r square, then omega I is omega j delta ij minus xj omega j xi dm. Now the reason we were doing all this, so that we could take out this omega j out of it. So that would mean you have r square delta ij minus xi xj dm into omega j. That's the only reason we had done this. Otherwise it would have been difficult trying to like simplify it further. Okay, now this is xi. Okay, now we have to defining ij a is equal to m r square delta ij minus xi xj to dm. This is 3.1. So HAI can be written as Iij about A into omega j. Okay, using this one. So this particular part is written as Iij about A, and this one remains omega j. So that's how we can write HAI as Iij omega j. Now we can use the index notation over here. So the summation has to be done over the repeated index, which is j over here. This would mean that I1 a omega 1 plus I 2 a omega 2 plus I 3 a omega 3. Okay, now the overall vector, this one, can now be written as HA is equal to, what is HA of I? That is Iij a omega j into EI hat. Okay, so clearly over here you will have 9 terms in total because there is a repetition over I and j. So if you keep on expanding, first with respect to j, then with respect to I, you will get the overall vector HA. Now let me demonstrate how it looks like. So first let me write this HA1. This would be equal to I1. I'm just using this one. Okay, so in place of I will just substitute 1. I11a omega 1 plus I12a omega 2 plus I13a omega 3 . Then you have HA2. Now in this one put I is equal to 2. That would make it I21a omega 1 plus I22a omega 2 plus I23a omega 3. Okay, then the third one HA3 is equal to I31a omega 1 plus I32 a omega 2 plus I33a omega 3. Okay, now I want to write this system of linear equation, this one, okay, in this matrix form. So HA1 HA2 HA3 is equal to I11A I12A I13A I21A I22A I23A I31A I32A I33A. Then you would have omega 1, omega 2, omega 3. Okay. You can also write the whole sort of in the vector form. HA is equal to IA into omega. This is 3.3. So over here, if you want to write, so HA will be equal to HA1 HA2 HA3. Similarly, IA would be essentially this. Please don't make me write this. Okay, it's a 3 by 3 matrix, and omega is omega 1, omega 2, omega 3. Okay, so this is just the matrix form of a vector, a column, so-called column vector. Okay, you should have known this form before. Okay. Now we had defined IJA is this 3.1. Now what you do is try writing IJI of A. Okay, what would that be? Let me do that separately. So Ij of A is defined as let me put again, defined according to 3.1 r square delta ij minus xi xj dm, then iji a, this would be, just interchange I and j in this, delta ji minus xj xi dm. Okay, now taking this forward, I can write this as r square delta ij. The reason is delta ij is a symmetric matrix. Okay, it's a diagonal matrix, so delta ji will be the same as delta ij. It's a unit matrix, and xi xj, this particular product can be written as xi xj. Okay, now this is actually equal to iij a. This implies that Iij of A is equal to Iji of A. So this is also a symmetric matrix. So the real symmetric matrix Ia is called the inertia matrix at A. Okay, this is relative to at A. Now just by looking at this expression, okay, we want to make a few points. One is that each of the components of this HA, okay, HA1, HA2, HA3 individually depend on all three components of omega 1 omega, okay, which is omega 1, omega 2 and omega 3. So each of the components of HA depend individually on the components of omega. That's the first thing. The direction of HA is this, okay, I mean it is in terms of E1, E2 and E3. Clearly you will you can write it in terms of repeated index, okay. So you have repetition over j, then repetition over I, so you can have this big form, but in general you cannot say that HA will be in the direction of omega, okay. So you cannot say that looking at this. So let me put that in red so that you can also verify it through some other way, okay. In general, HA is not in direction of omega. I mean, one easy way to see if something is in direction of the other vector is just take a cross product, okay. If you take a cross product of two vectors and they are pointing to the same direction, you would get a 0, okay. So that's one way to check, and perhaps you can make that check. Like a proof by contradiction. Okay. Now if you do happen to have a point B which is not on this rigid body, so for a point B not on the rigid body, you can write HB. This is something which you know already, several times we have done this. RCB cross MVCB. Now even if after that you do not recall, please pause the video right away and go back and check why we can do this. That if for a point B not on the rigid body, you can write it in this particular form, okay. So I haven't really shown, but let's just put our center of mass somewhere over here, okay, HC. Now since C is as good as a point as A, we want to write this HA, okay, this particular HA 3.2 over there. So we would write it as IIJC omega J EI. So we will write it as IIJC omega J EI, okay, plus RCB into MVCB. Okay, now the reason we had done all this exercise over here, because this form, this 3.3, is actually very simple to use. Okay, and it is especially simple to use if for some reason this term, this term, this term, this term, this term, this term becomes 0. So you only have the so-called diagonal terms remaining. Okay, so it will become, because then you would have very few terms out of this. Okay, you would just have, say, HA1 will be I11A omega 1, that's all. HA2 would only be I22A omega 2, and HA3 would be I33A omega 3. Okay, so we want to see how that can be done. Okay, how can we basically diagonalize this IA matrix? Okay, just so that it becomes much more simpler. So equation 3.3 is very simple with respect to axis at A for which IA is a diagonal matrix. Let's now do that. Okay, so this is done next. I mean, it's not as straightforward, so we'll have to go through some struggles of mathematics before we do that, but when it's done, it will be really in a form which is very easy to use in most of the engineering applications. So let's discuss the so-called inertia tensor at A. So until now we had something called the inertia matrix, okay, which looked like this. Okay, and we are now discussing this inertia tensor. So let's see what it is. Now, other than this body, let's I mean, we have already drawn this, right? It's a whole body of mass m. We have taken a small mass dm, okay, and like this. So let me do something else over and above this. Let me take this as m, dm e2 hat e1 hat. Okay, I don't want to draw a line like this. This is better. Okay, so the same point P is shown, small mass dm. This is RPA. This is A, and this would be equal to XI hat. Okay, now take this mass P, okay, MP. Clearly we could have used a different symbol over here, but this is the thing, this is a capital P, okay, and this is a small p, okay, so this vector would be small p a. Okay, I'm sorry it doesn't look better than this, but it could have been uh, better used. Okay, once this is done, we can write this vector as x pi ei hat. Okay, then you can say that you have a mass 1, you have mass n. Okay, so p is this, mp is this generic mass. Now this is the trick. If the body other than what it is, okay, other than this having a mass m, if it includes n mass points mp at r small pa equal to x small pa, sorry, small xpi ei hat, then this summation for p equal to 1, this is the first point, to p equal to n, this is the nth mass. Okay, this r small pa square delta ij minus x small pi x pj. Okay, so I'm just writing this ija term, okay, for all of these masses. Okay, now so this quantity which you have, okay, we had defined this as iij about a, and these are for these single masses m1 m2 m3 until mn, mp being the generic mass. Okay, then this quantity is added to RHS of equation 3.1. okay, so let's see 3.1. okay, so you have to just keep on adding. So this was for say a distributed mass. Okay, now if you keep on adding those m1 contributions due to m1, you will have lot of terms. So that sigma summation which we have written over there has to be added on this side. Okay, so that part is clear. Let me just remove this also from here. Okay, so dm can have many forms. It can be a lambda ds if the mass is distributed over a curve. It can be sigma dA if mass is distributed over area, or it can be rho dV if the mass is distributed over a volume. Okay, so you have done this several times. So depending on the situation, you can do either of them. Okay, now let me write ia11, the first term. Okay, just recall 3.1, put I equal to 1 and j equal to 1 on that, and one would get r square delta 11 minus x1 square dm. Okay, this can be clearly written as r square, remember, will be equal to x1 square plus x2 square plus x3 square, and delta 11 is equal to 1, so this would become x2 square plus x3 square dm, or this would be Now now what I'll do is I'll draw a cube over it. Sorry. Okay, and then yeah. Okay, yeah, this is better. So let's have this point as say q. This particular distance from q to p, okay, it's clearly perpendicular to this axis. This distance is what is varying along this distance? X2 square plus x3 square whole square. Okay. Similarly, this distance will be x1 square plus x2 square, and then you can have, say, this distance x1 square plus x3 square. Okay, so that's why when we were writing I11 is equal to x2 square plus x3 square, this can be written as pq whole square dm. Okay, so you can look at this distance pq. Okay, I'm not showing the other points, but I hope you can get the idea. Okay, so this will be 90 degree and this will form a 90 degree with this E3 axis, and PQ will form a 90 degree with E1 axis. Okay, okay, this would be x1 comma 0 comma 0, and this will be x1 comma x2 comma x3, hence the distance PQ square will be x2 square plus x3 square. Okay, now once this is done, you can now proceed with equation 3.1. Sorry, I should now come back to black. Square delta 1. So put I equal to 1 and j equal to 2 in equation 3.1. That should give us x1 x2 dm, and as you know, delta 1 2 is equal to 0, so we have minus of x1 x2 dm. Okay, now the third component would be I13. So you have to keep on proceeding like this, put I equal to 1, j equal to 3, and so on. So for all the 9 terms, one would proceed like this. Okay, so what I'll do now is I will write all the expressions and you should individually verify them. That's why they will all be in red. So I11 a is equal to x2 square plus x3 square dm I12a is equal to I21a is equal to minus of m x1 x2 dm. I22 of a m x3 square plus x1 square dm. Okay, and I23. So one way was, I mean, we had already shown that ij is the same as iji. So you perhaps don't have to separately find I21 once you have found I12. Okay, maybe you can do it once just to verify and double check, but it's not really needed since you have shown that I is a symmetric matrix. Minus of x2 x3. Then you have I33a m x1 square plus x2 square. I31 is equal to I13, that would be m x3 x1 dm. Okay, so this is all equation 3.5. Okay, so 1, if you remember, is the E1 direction, 2 is the E2 direction, and so on. So you can write this in x and y format also. So xix will be, I'm just taking this one, this will be m of what is x2 is y, what is x3 is z dm. Okay, this becomes m kx kx of a whole square ixy is equal to iyx of a is equal to minus of m xy dm. Z square plus, so I'm looking at this one now, I22 z square plus x square d, okay, this is dm is equal to m into kya whole square, and I, this one yz a is equal to izya is equal to minus of myz dm. Okay, and this is equation 3.6, all three of them, or as many of them, 9 of them actually. Okay, and the last one would be izz of a x square plus y square dm m kz a whole square I z x a is equal to I x z a minus of m zx dm. Okay, so a few more sort of definitions being thrown at you now. I11 of a, I22 of a, and I33 of a, or Ixx, Iyy, and Iz. These are called the moment of inertia of rigid body, or actually any body, about x1, x2, x3 at A. I12, I23, I31, I21, I32, I13, they are called the products of inertia. Okay, everything else remaining same with respect to the axis about A, okay, or at A. So point A is over here, okay. Okay. Similarly, if you have like the n mass, I mean, we didn't actually, we discussed this briefly, but we didn't actually write them over here. So if there are n mass points, okay, then they have to be added to these terms, okay. So if n mass points are present, then appropriate sums are added in equation 3.5. okay, this is 3.5 in red. For example, in this one you will be able to add summation over p xp2 whole square plus xp3 whole square mp. Okay, so in this particular term you will again be adding this summation minus xp1 small p, okay, small p, and xp2 mp. Okay, so you can keep on adding the terms in all of these, okay, if there are these mass points remaining. So I'll just remove this for now. What will happen is that, I mean, you may know this answer directly, but the geometry of the problem or the rigid body itself will have some sort of a exceptional or an extra mass points, so you can add them, their contribution to this inertia separately. Okay, equation 3.5. Okay, now look at these terms in black. You want to write INNA, okay, no repetition over n. So this is a convention which we follow to basically represent this Ixx, Iyy, and Izz. Okay, we write it like INN, and ISS. Again, no repetition over S. So this, I'll define what these two quantities are. Let me show this. Yeah, this is better. The mass moment of inertia INNA about a line with unit vector n through A is defined as INNA is equal to m t square p dm. Okay, where this dp is the distance of p from line NN through A. Okay, so the A is always there. So let me show this diagrammatically. If you have, say, total mass is m, a small point is, sorry, the small mass is dm, this is p, okay, so this is the line NN in which we are concerned with. The point A, it has to pass through. This distance is dp. Say if you have this additional mass m1, additional mass mi, okay, then this will be di mn. Okay, so in this case INN will be equal to dp square dm. Now if you have this additional masses m1, m2, n3 and so on, then you will just keep on adding the terms like multiplied by just what di square into mi. Yeah, I'm not putting that over there, but you can keep on doing this. Okay, so this is the meaning of INN of A. Now this quantity, if you can just look at this integral, will always be greater than equal to 0. Okay, because it's a squared, dp is squared. And when would the equality hold? If dp is always 0, or all the mass is on line NN. Okay, if all the mass is on line NN, then dp will always be 0 for all the individual terms. Then you can say that INN is equal to 0. So Ixx of A plus Iyy of A, if you can see this, Ixx of A and Iyy of A will be what? X square plus y square plus 2z square, right? So this would be mx square plus y square plus 2z square dm, and this will be greater than Izz of A. Look at what Izz of A is. It is only x square plus y square. So 2 times z square will only make this larger, and that's why this ixxa plus iyya is greater than equal to izzza. Only it will be 0 in a case in which this z square dm is always integrating to 0. Okay, that would be equality holds. Only if z is equal to 0, that is mass distribution in plane xy. Through A. Okay, and also remember here we had sort of written this in terms of this kx, ky and kz. So let me define that as well over here. So the radius of gyration kNa of a body of mass m with respect to an axis n at A is defined. Okay, these are all defined entities as the distance from that axis at which discrete m can be placed. To have same INNA about that axis and as given body. So what this means that if you have m k n a whole square, this would be I n n a. This implies that k n of a is equal to I n n of a by m one by 2, okay, into kx. Sorry, kn square is INNA. Okay, now this means that we had represented actually not in terms of n but in x and y. So remember kxa, kx, so kya and kza are radii of gyration about the x, about x, y, z axis at A. Okay, so that's what we had written, and this is how the radius of gyration is defined. So many a times, I mean, the radius of gyration is given, and one has to say come up to this INN. Okay. Now over here, I mean, if you look that Ixx plus Iyy will be equal to Izz if the mass is distributed along the plane xy through A. Okay. Now this definition is important because if this point A or so called is not in this plane, then it won't be really true. Okay. So Izz of A equal to Ixx of A plus Iyy of A. Okay. Iyy of A as z is equal to 0. Okay. Mass distribution on a plane area in the xy plane with A in this plane. Now this is not for any point. So if you have, say, a point B not in xy plane, then Izz of B is not equal to this. So you have to really be careful about this. Okay. The point A about which these moments are calculated has to be okay. So okay. We also now want to discuss the transformation relations. Okay, let's call it as transformations. So we have defined this quantity, say I PQ at A of inertia matrix. Okay. So this was IA, like this means that it has 9 components. Okay, I11, I12, I31 and so on. Of course there are some equalities, but it has a total of 9 components. Okay, now this is with respect to convenient access xi ei hat at A. Okay. So let's try to see what the transformation relations would be. So if you have, say, Iij given, what would be Iij dash? Okay. And what's the meaning of this transformation is not very difficult to understand. Think of like vectors. Okay, see, they have this vector. This is I direction, this is j direction, and you have this vector called, say, 2I hat plus 3j. This is a position vector. Now if I have another coordinate system, say I dash, okay, and j dash, and then I ask you what is this vector. Okay, then you will have to say, let me not call it 2 plus 3i, but let me call it as sort of ai plus bj. Okay, now I have this transformed coordinate system which is I dash and j dash, and I want to know what would be the vector in this green coordinate system. So a dash I hat plus b dash j hat. Okay, this is what we want. Now what we are looking for is the relation between a dash and a and b, or b dash and b and a. So basically, what is the relation between a dash and b dash and a and b? So that is what we are trying to do over here. Now we do not have a sort of a vector which has these two components a and b. We have now a matrix, and this one would have components of ij. What would be the components of this ij dash primed, whatever you want to call it, in terms of the old components? Okay, and obviously the coordinate system over here will also change. So here it would be, say, xi, here it would be xi dash, or here it would be ei, here it would be ei dash. Okay, so ei dash is equal to, now let's draw a nicer diagram. Okay, e2 hat, e1 hat, and e3 hat. Okay, you have this mass m, you have this point P, this is small mass dm. Okay, and then let's just, okay, this is point P. Now I can write this vector RPA in terms of the basis vectors e1, e2 and e3. Let that be equal to xi ei hat. Okay, now let me draw another coordinate system. This would be e1 hat dash, okay, e2 hat dash, and e3 hat dash. Okay, now this same vector RPA, okay, just like over here, this can be represented in the green coordinate system. That way we would write it as xi dash ei dash. Okay, the same vector is like this. Okay, and this point is again a, about which, okay, so we can write the same vector RPA in terms of the black and the green coordinate systems with their own basis vectors, as you can see. Now ei dash, so what I want to do now, I want to write this vector, say e1 dash, e2 dash and e3 dash in terms of e1, e2 and e3. Okay, so what you have to do is this: visualize this one vector e1 dash. Okay, it's a unit vector, so it's still a vector, and you have to write this in terms of let me, So this is E1 dash. You have to write this vector which I have marked with red in terms of the black coordinate system. Okay. So just like we could write this vector RPA in terms of black coordinate system, we can also write this marked red vector in terms of the black coordinate system. So I want to write it as E1 dash is equal to, say, A11 E1 plus A12 E2 and A13 E3. Okay, no harm in this. Similarly, I can write the vector E2 dash, this one, in terms of the black coordinate system. That would be, say, written with these two. So I am writing these coefficients very carefully, but you can, I mean, if you have an objection at this stage, you can just call it as, I don't know, A, B, C, then this is D, E, A2, sorry, E2, okay, plus F, E3 hat, okay, and similarly E3 hat can be written as G, A31 plus H A32 plus I A33. Okay, so you have to have these three scalar components ABC, three scalar components DF, and three scalar components GH I, because these E1, E2, E3 are now their basis vectors in the terms of which you are writing E1 dash, E2 dash, and E3 dash. Now, sorry, this is okay, this is correct. This should be E3 dash, E2 dash, and E1 dash. Okay, this is what we wanted to write. Now what I want to do is I want to replace these scalars by some convenient numbers, which is A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, so you have A33. Now this in the most general form can be written as A1 EI dash as AI1 E1 hat plus AI2 E2 hat plus AI3 E3 hat. Okay, and I mean you can just replace, say, I equal to 1 and then you will get this expression. Just put I equal to 2, you will get this expression. Put I equal to 3, you will get this expression. Okay, now this can be written as AIP EP hat. Okay, this is equation 3.17, sorry, 3.7. Okay, now AIP is, as you know, the component of EI dash along EP. Okay, how do I know this? Let me take up, say, A12. This is the component of E1 dash dot E2. Okay, EP is 2. Okay, now what you do is take a dot product of E1 dash with E2. Okay, take a dot product of E1 dash and E2 and you will get A12, which is it over. So that's why it is said that AIP is the component of EI dash along EP, or EI dash dot EP. Or this can also be written as the cosine of the angle between EI dash and EP This is called the direction cosine of EI dash with respect to EP. Okay, now let's write equation 3.7. EI dash is equal to EIP AIP EP. Okay, and we can now just write this in terms of J also, since you can say that J also goes from 1 to 3, so it is the exact same expression. Okay, and we can also get rid of P and write it Q. Okay, you will see the reason for doing all this in a few moments, but the idea is that this is the same as equation 3.7, what is written in front of you. So if you write this three equations and write this as three separate equations, they will be the same exact equations. Okay, now delta ij dash is equal to ei dash dot ej dash. Okay, this is something which we already know, so e1 dot e2 is equal to delta 1 2. Now ei dash we want to write from over here, that is aip ep. Okay, this has to be dotted with ej dash, which is over here, so this would be ajq eq. Okay, this can be written as aip ajq delta pq, because ep dot eq will be delta pq. Okay, now rpa is equal to xi ei hat equal to xi dash ei dash. This implies that rpa dot rpa is equal to r square. It will also be equal to r dash square. Okay, so x1, I mean the logic is that the length of this vector pa, okay, that is equal to x1 square plus x2 square plus x3 square, and the length of this vector remains the same irrespective of in which coordinate system you write it. So in the green one it will be x1 dash square plus x2 dash square plus x3 dash square, but they will be the same because the length of the vector is not changing, the magnitude of this vector is not changing. So that's why we have r square is equal to r dash square. Now xi dash is equal to rpa dot ei dash is equal to xp ep. Okay, I have just written xi ei as xp ep, okay, into ep dash, ei dash. The reason I didn't like write this as p also, though it would have been I mean okay, is that then it would be like a summation with 3 repeated indices that is not defined. Okay, so we only want 2. You will get the hang of it as you keep on doing. Okay, now xp ep dot ei dash is equal to xp into aip, just by looking over here. Where did it go? Here. So EI dash is equal to AIP EP. This has been used. So what has been used? Equation 3.7. So please figure this out. I think it should be very easy for you to do. Okay. This implies that xj dash is equal to AJQ XQ. Just replace I with J and P with Q. You get the same thing. So when I say replace P with Q or I with J, they are all called dummy indices. Okay, because they mean the exact same thing, just that the separation. But you have to make sure that the dummy index can only appear twice. It appears only twice. Okay, now you want to use this equation 3.1. 3.1 is where we defined Iij. This one and the transformation ones which you have just defined over here at A. Okay, so use 3.1 and A. Let's see. So 3.1, let me just write 3.1. Okay, Iij of A is equal to M R square delta Ij minus Xi Xj dm. Okay, so you want to now write, say, in a transformed coordinate system. That's why I'm showing with this dashed symbol. What changes? Well, r square becomes equal to r dash square. Please keep on looking at these equations A. R square becomes equal to r dash square. Okay, delta Ij can be written as delta Ij dash. Xi will be written as Xi dash Xj dash. Okay, dm. So this is basically written in terms of the transformed coordinate system. Okay, the same definition is written over here. Now we will be seeing the relation between this and this. Okay, so for this it's quite easy. Put xj dash is equal to so what you have to do is write this using this. Okay, so let me help you do that. First thing is r square, sorry, r dash will be equal to r. So r square delta ij will be delta ij dash will be equal to delta ij minus xi dash is what? Xp aip. Xj dash is equal to ajq xq dm. Okay, this is using A. Now this can be written as r square delta ij minus xp okay, and then this will be tm. Take the AIP actually this coming from here to here was not that straightforward. AIP AJQ. Okay, so this is something which you should now try to check. How did you come from here to here? I think we should have done it at some place, but if not, I mean, you already know that delta ij dash, where did it go? Over here, delta ij dash is equal to AIP AJQ delta PQ. So that has been used over here. Okay, so it's not delta ij dash is not equal to delta ij. Okay, okay, so that's good progress. This means that ija dash is equal to AIP AJQ IPQ Okay, so this is how it looks like. The transformed moment of inertia looks like this. Okay, and what are this AIP and AJQ? Well, they come from directly here. This one. Okay. So you can see that there are 9 terms on this, because both P and Q are repeated. So I want to write this in the matrix form. Is equal to AIP AJQ IPQ AIP. Okay, now this IPQA can be written like this. Okay, no problem with this, and A can be written in transformed form of QJ. So what has happened is that you have just represented it in this matrix form. It has to happen because, I mean, for this matrix multiplication to happen, this P has to occur over here and Q has to occur over here. So once you bring this in the middle, you will have to transform this, otherwise it will start look like this. Or even though summation wise this is okay, summation wise this is okay, but in the matrix form this will not make sense because you should have a Q over here. So you have to, the only way is to write it as Qj, and AQJ can be written in terms of AJQ just by a simple taking a transpose. So that's how it has been written in the matrix form. This is in the matrix form. This implies I A dash is equal to, in the matrix form, A I A T. Okay. So any quantity, for example, in the EI system, EI coordinate system should be denoted by this. Anything in the EI dash system should be denoted like this. Okay. So let's now define tensors. Okay. The most general is that a tensor follows a transformation law like this. Okay, that's the most sort of accurate definition, and let's now try to build up a scalar. Okay, for example, temperature T with 3 raised to the power of 0, which is one element, such that T dash is equal to T is called zero order tensor. So every matrix is not a tensor, but every tensor can be represented as a matrix. So until now we had been referring to this moment of inertia matrix, but since it follows this particular transformation law 3.9, we will be actually calling it a tensor. And if you say put temperature over in this law, you will find that the temperature in the transformed coordinate system and the original coordinate system is exactly the same. So this is a zeroth order tensor. Say you have a vector, okay, like say RPA, the position vector, with 3 to the power of 1, which is 3 elements. Okay, a vector will have 3 components, such that xi dash is equal to AIP into XP. Okay, remember the vector RPA was written as XP in terms of XP. So XPEP. And this is something I think which we have seen somewhere over here. XI dash is equal to XPAIP. Okay, this is the transformation law for a vector and is called a first order tensor. And then you have, say, an entity defined entity. Remember we defined it at the start of this discussion, like IA with 3 to the power 2, 9 elements, such that IJ A dash is equal to AIP A JQ IPQA is called a second order tensor. Okay, so you can just keep on seeing this power of 3. Okay, and similarly, say you have some other quantity which follows this transformation law dijk dash is equal to aip ajq akr dpqr. This is a third order tensor, and it can keep on going up. For example, you have Cijkl dash is equal to a ip ajq a kr a ijkl pqrs c pqrs. This is a fourth order tensor. Of course, we don't have to go this far, okay? Until here is what we need over here. But you should just know that all of them will be called this tensor because they follow this transformation law. Just like if you remember, a vector is a quantity which has a magnitude and direction, and it follows certain transformation laws. Okay. By the same logic, you would say that the angular displacement, or the so-called rotation, is not really a vector; it's a pseudo vector. Okay. So that's where angular displacement loses out, because it does not follow one transformation law which it should. Okay, that's why it doesn't qualify as a vector. Okay. So now you can come back to this figure which we had drawn, just trying to motivate ourselves that what would be this Iij in the green coordinate system. We now also want to define what Inn would be in the in this system. So let's write that. So we want to have, say, this Inn of A about an axis N, which looks like this, NP EP at A. This is obtained using this equation which we have just derived, 3.9. Okay, so just remember this. So E1 dash in this case will be equal to A1P EP. This is equal to N. A1P is equal to NP. Now Inn at A will be equal to I11 of A dash. This can be written using this transformation law 3.9 as A1P A1Q IPQ A is equal to NP NQ IPQ A. Okay, just because AIP is equal to NP and AIQ will be equal to NQ, so this has been written. Now you want to clearly expand this, so you will have these 9 terms. So let me write that. INNA will be equal to I11 AN1 square plus I22 N2 square plus I33 n3 square plus 2 times of I12a n1 n2, 2 times, because this I12 will be the same as I21. So we will have a I12 n1 n2 and I21 n2 n1. So both of these terms are the same, so they can be just written as a 2 time. Similarly, 2I23a n2 n3, okay, plus 2I3 1a n3 n1. This is equation 3.10. okay. Now you want to write the product of inertia. We have written the moment of inertia and product of inertia before. Please check that. INS, okay, about orthogonal axis N and S. So S can be, say, equal to SQ EQ at A. So for example, if this over here E2 dash is equal to S, okay, so yes, this would mean that A2Q will be equal to SQ. So A21 will be equal to S1, A22 will be equal to S2, and A23 will be equal to S3. E2 dash, okay. So you have to refer to the figure which we have just drawn. So E2 dash will be equal to A2Q. Sorry, this doesn't come over here. Now after this, if E2 dash is equal to S, okay, then this can be written as A2Q EQ, that is A2Q is equal to SQ. Now INS A will be equal to I12 A dash equal to A1P A2Q. Same transformation law which we had derived. IPQ of A, this is equal to NP SQ IPQ of A. So A1P is equal to NP from over here, and A2Q is equal to SQ. Okay. Now NSA is equal to IPQA NPSQ. We have to now write it in the expanded form because there's a repetition over P and repetition over Q. We'll say that I11 of A N1 S1 plus I22 of A N2 S2 plus I33 of A N3 S3, okay, plus I12 of A n1 s2 plus n2 s1 plus I23 of A n2 s3 plus n3 s2 plus I31 of A is equal to, sorry, 31 of A is n3 s1 plus n1 s3. Okay, so the answer is just, just repeat it and you will have all these terms. Now some of the terms are actually invariants. Some, invariant, I will explain what invariant is. What it means is that no matter what transformation your coordinate system goes through, the value of this invariant does not change, and that's why it's called an invariant. So under any transformation, this particular value will remain the same. So one example which is somewhat popular is IA is invariant. Okay, this means that I11A plus I22A plus I33A. Remember, we are now using this summation because it's not n or s. If it was I and n, then we wouldn't go for this summation. This value is equal to, say, 2 times of, if you can check the expressions written in red, they were in equation 3.5. You will write what I11 is, that x1 square plus x2 square plus x3 square dm. Okay, and you have to find what I22 is and then I33 is. So all three of them, if you write, you will get 2 times of this integral over m x1 square plus x2 square plus x3 square, and this is the same as 2 times of, say, m r square dm, and this quantity can be written as, this quantity can be written as I11 a dash plus I22 a dash plus I33 a dash. Okay, so I11 a plus I22 plus I33 is the same as I11 dash, I22 dash and I33 dash. Okay, so that's why under any transformation this summation will remain the same, and there are several more forms of this. This is not the only invariant, but you should be aware of what this means, this invariant. Okay.